So previously we had seen the pigeonhole principle, we proved it. We've seen two different ways of formalizing the pigeonhole principle, namely in terms of objects and bins, and we also talked about, with some discussion about functions, how we could describe the pigeonhole principle in terms of functions. Namely that the pigeonhole principle, instead of talking about there being a bin with at least two objects, in that case it's that there is no bijection, meaning it's not bijective. So I want to show you a couple of basic examples first, just so we can see what we can do with this pigeonhole principle. So I thought we would start off with some examples. And one classic way of playing around with the pigeonhole principle is by taking large number statistics. Suppose that I give you a group of people. I would like to be able to say something about that group of people with respect to some category that all of these people have. So let's start with a basic example. I'm going to refer to this fun bit of discussion we're going to have as meeting of birthdays. So as per usual, if you want more discussion about some of these things, they're in the notes, okay? So I'm sure if I gave you a group of people, we can agree that everybody has a birthday. So everybody has a birthday. I mean, even including you guys, those ones on the leap year. I understand. Everybody has a birthday. The day of the year that person is born. So days in a year are organized by month, right? In the Gregorian calendar, there are 12 months. We're going to refer to the birth month as the month for which a person is, the person is born within, okay? The birth month, sorry, I'm getting really excited here. The birth month of a person is one of the 12 months I'll say they were born in. I'll say a person. We'll say a person was born during. For example, if you're born in the month of March, your birth month is March. Hopefully that's clear, everybody. So if I give you a group of people, suppose I bring together a group of 13 people. So suppose that we're given, sorry, I'm getting really excited. My given is sort of melting over here. So suppose that we're given a group of 13 people. I have a question for you. If I give you 13 people, any 13 people, I have a question. Question. Do at least 2 people share the same birth month? So if I give you 13 people, do there exist at least 2 people that share the same birth month? Well, let's see. Let's try to kind of visualize this a little easier using some of the things we've talked about previously. So I have 13 people. We have 12 months. So I'm going to have some people. So I have these are going to be my objects. So I'm going to have 13 of them. I have person 1, person 2. I'm just going to assign them names just to make this easier to play around with. Person 12, person 13. So I have 13 people. This is my group of people. And also I have birth months, right? And these are my bins. So let's see. So we got January, you got February, you got March. I'll keep it, I have to pick either abbreviations or full, so I'll go abbreviations here. March all the way up to December. We got the 12 months. Those are our bins. And we agreed that everybody has a birthday, and it's going to fall, like whether you want to round it or not, regardless, somebody's got some birth month they can associate themselves with. So let's describe how that might play out. So I can have each person is going to be associated with a birth month. More formally, I could describe this actually as a function if I wanted to. So I'm going to call the function capital P. It's going to take in a person as input. No, don't think about like the machine picture. It gets a little graphic. Let's try to just imagine it more that we just know that each person has a birth month. Okay. So this is the birth month. So it just tells you the birth month of person PI. So it tells you the birth month of person PI. So you could imagine it's just like a table with all the people in this group. Each one, it tells you each person with their birth month right beside it. So you can just imagine it's like a lookup table. So we've identified objects and we've identified bins. We've identified how we're going to put the objects into the bins. But what can you say about our objects in bins now? Well, normally a good strategy for applying the pigeonhole principle is to identify the objects, identify the bins, and identify the relationship between the objects and the bins. If it characterizes the pigeonhole principle, then you're all hunky-dory to play around with the pigeonhole. But you have to be very careful when you use the pigeonhole because remember, these are objects, those are the bins. I need to be able to put the objects into the bins. It isn't that I get an option to not put them in the bin, right? They all have to go into some bin. Like everybody here has a birth month. Nobody's just gonna be like sitting off to the side saying, I don't have a birth month. And remember, the beauty of the pigeonhole principles, I don't know how these exactly are assigned. I could, for example, hypothetically speaking, I can have a group of 13 people where everybody is born in January. That is a possibility. Likewise, there could be somebody that like half of them are born in September, half are born in, I don't know, in April. That's a possibility too. These are all different possibilities. The pigeonhole principle, however, tells you that there's going to be at least one birth month that has at least 2 people that share that birth month. It's because their birthdays during that month. So yes, by the pigeonhole principle, at least 2 people in the group, just to be clear. Not just any 2 people, it's just in this group of 13 people shared the same birth month. Pretty neat, right? That's a pretty good place for us to start, right? Like the whole idea is that there are not enough birth months for my people to all be able to be distributed such that they're all in their own birth month. So I already see that. So notice that you can also extend this. So if you wanted to have 15 people, the fact is still true, right? As long as there's at least 13 people, you can get away with this. Now what if you had it, what if you had, let's ask a similar question. Let's ask a similar question. They share the same birth month, but how about the same birthday? How about the same birthday? Can we say that? Using the pigeonhole principle? Any suggestions? Can we use the pigeonhole principle here? It's instead of asking the question, if I give you 13 people, any 13 people, and I ask the question, are there at least going to be 2 people that share the same birthday? Can you guarantee that under the pigeonhole principle? Well, let's think about it. Let's look back at how we characterize the objects and bins. Because remember, the objects are the people. The birth months were the bins. Now, for this question, we'll need to swap out the birth month with the birthday. So, can we use the pigeonhole principle to justify that there's at least 2 people in any group of 13 people that they share the same birthday? No, right? That we don't have enough people to guarantee such a thing. Because when we swap this over to birthdays, so when we have birthdays, now I'm talking about a day during the year. So we're talking like January 1st all the way to the last day of the year. Now, how many days are there in a year? At least in the Gregorian calendar. Now, I'll warn you that this is a little bit of a trick question. I'll give you a moment to think about it. So, while you're thinking about that, I can answer this question. You can say no, because we just don't have enough people. But I want you to think about that. Not enough people. Now, how about if I generalize this question a little bit further for you? Just to make it a little easier to answer the question. Okay, what about if it's an arbitrary year? Not just, say, a year where a leap year isn't. What if it is the case that we land on a leap year? That means that, suppose that there is a day for which we have an extra day in February. So how many people then do we need to get together? At least for any arbitrary year. So how many do we need? So that's the question, because we lack a number of people. So the days in the year, so how many days in a year? Well, on a typical year, if we're talking like physics, it's approximately 365. It's an approximation of this. But what happens as a result is that in the calendar, what happens is every so many years, we have to make up for that little bit that's on the end of 365. And that's why we have leap years. So, but because of that, this is at most 366 days in a year. So how many people should I get together then to guarantee we can use the pigeonhole principle? So think back to my picture up there. My bins are the birthdays. So the days of the year. Well, now you could see that the number of bins is going to be at most 366. So if I give you 367 people, that will be enough, regardless if it's a leap year or not. So if you get me at least 367 people, that's enough to think about. So I'll let you think about that. In fact, I encourage you, if you could somehow get 367 people together, I can't today. I can't fit that many people in this room, okay? It's not that big. If I could, we could take 367 people. We can ask them what day of the year they were born. And the Pigeonhole principle guarantees at least 2 of them are going to share the same birthday. Pretty nifty, right? So do you notice the exercise is quite simple? But you have to be very careful, right? Because remember, it's the kind of relationship that exists here. Is that every person has a birthday. Every person has a birth month. Every kitty has a box. That's what we're talking about here. So the point is that we have to identify the objects, the bins, and then there's going to be some function that's underlying this that is going to describe how we assign the objects to the bins. Or equivalently, one finite set to another finite set. And then we check the conditions of the Pigeonhole principle. I'm going to take and address this question to Winnipeg. Got some lovely Winnipeggers. For those that aren't aware, a Winnipegger is someone that lives in Winnipeg. So let me let's talk a little bit about this. Let's do this. So at the time of making this video, and I must stress that technically it might be more depending on how generous you want to be about the boundaries of Winnipeg. You can always use some more up-to-date statistics from Statistics Canada, for example, if that is something that you need. But the population of Winnipeg is at least 713,000 these days. Now, here's another thing. So this is just a fact. You're more welcome to check it. So it's at least that many. How about this? Now, let me throw another interesting factoid to you. Now, you'd agree with me that humans have hair on the top of their heads. They may have no hair. They may have at least one hair follicle on their head. They may have more, right? The point is every person, including every Winnipegger, has some number of hairs on the top of their head, right? So this is just fact 1. Fact 2 is that humans on average have 100,000 hairs on the top of their head. This varies depending on your hair color, for example. From at least what I've read, and I had to do a little bit of digging for this. From my understanding, depending on the color of your hair, at least on large population averages, the amount of hair follicles you have can differ. For example, a blonde-haired person may have more hair than somebody that has brown hair. At least on the top of their head. That's at least what we're talking about here. But, so it may be up to, for this average, for 150,000. That's namely for the blondes. So regardless, I'm just going to be overly generous, and I must stress that if, say, for some reason there's somebody with even more hair follicles than this, the argument will still hold. It doesn't matter that I just picked this number. It could be even higher. It doesn't have to be that much higher than this. You can go up to 300,000 if you wanted to. I'll just make it this is at most 200,000 hairs. It's definitely a bound that's going to be okay enough for us, at least here. But if you want to make this 300,000, you want to make it 400,000, if you want to make it 500,000, that's okay too. Like I said, it's usually like if you look at the surface area of somebody's scalp, you could do some basic calculations from physics and you'd find that, yeah, it's roughly something like this. So to expect it to be somewhere way out here is going to be quite the anomaly. Is that every Winnipegger has 0 or more hairs on the top of their head. So you have an idea where we're going with this. So you can imagine I gave you the people of Winnipeg. So remember, we identify the object, identify the bins, and the fact that every Winnipegger has to go into one of these bins, because it's quite natural we're going to talk about Winnipeggers. So we got our people. So these are my objects in the example. Objects, and we're going to have hairs on the top of your head. These are going to be the bins. Now remember, there could be somebody that has no hair on their head, they're bald, or they have some small number like me. Some smaller number. But the point is, we're just going to be generous. We'll throw some more categories of numbers of hairs in there as well, just to play it safe. But keep in mind that number could always be higher if we wanted it to be. But not too much higher. But if you understand how we're going to use the pigeonhole principle here, if we can, you'll see that it really doesn't make much of a difference. So I'm going to label out the people. Okay. So I've got my people. I got hairs on the top of your head. So how am I going to describe this? Well, we said that every Winnipegger has 0 or more hairs on the top of their head, right? So let's describe this now. So T of PI is the number. So for a given person, it's the number of hairs on top of PI's head. So I'm going to throw some fun facts at you. The population of Winnipeg is at least 713,000. Humans on average have about 100,000 hairs on the top of their head, but it may be up to 150,000 on average. But for generous, we're going to keep it at most 200,000. Well, the people are objects in my application of the pigeonhole principle. The number of hairs on the top of your head are bins, and the number of hairs is simply characterized by this function. Because every Winnipegger has 0 or more hairs on the top of their head. Like me. I don't have as many. But the point is that you get a very, very interesting revelation that comes out of this. Is that, so by the pigeonhole principle, at least 2 Winnipeggers have the same number of hairs on the top of their head. Have the same number of hairs on the top of their heads. We'll say head. So that's so those are some interesting examples of how we can apply the pigeonhole principle for large groups. This is one way you can use the pigeonhole principle. So for example, if you're working with ingredients and you're asking how many ingredients you have to fit a certain number of pizzas, or something along those lines as well, like there's a lot of ways you can pack things from items into bins or objects into bins. This sort of packing stuff I think about all the time. But the point is that you can apply the pigeonhole principle when you have sufficiently many objects. You get really mind-blowing conclusions kind of like this that you never really think about in your daily life.